Start recording this webinar and welcome you all officially to today's webinar, Changing Narragansett Bay, exploring changes to eutrophication and finfish communities with a focus on Mount Hope Bay. I am Courtney Schmidt, the staff scientist with the Narragansett Bay Estuary Program, and I will be your host today. So without further ado, I'm going to ask Dan to share his screen and he can start his presentation. And while he's doing that, Dan is, well, he really wants you to read the report this is based on. He worked really hard on it. He comes to us as an independent contractor and has an affiliation with URI. And he spends a lot of his time thinking really hard about how to make sense of a lot of the data that we receive from our fixed site monitoring network here in Narragansett Bay. And without further ado, take it away, Dan.
Okay, thanks, Courtney. Can you hear me?
Yes.
Okay, great. Well, yes, thanks for the opportunity to talk about this work I've done recently. Title of the talk is a little bit long, unwieldy, but a changing Narragansett Bay, synthesis of bay-wide eutrophication-related conditions and influences using multiple data sets and metrics. So the first thing I want to start off with is just to express my thanks to so many different people from so many different organizations and institutions. I've been working with a huge amount of data from a lot of different sources and programs, and everyone's been really generous with it and helped me a lot in terms of understanding the context for the data and how to analyze it. So I just wanted to make sure everyone knows that I appreciate their help. And also, as Courtney mentioned, if you're doing research on any of these data sets, the spirit of the report is kind of an open science sort of thing. The report includes documentation of all the data sets, as well as all the code that I wrote in order to interpret them. And many of the files are posted online along with the report. So if you're curious about the data or you want to work with it, if that's what it's there for, and I'd be really happy to have anybody come and get it and work with it and let me know what you find out about it and what kind of research you can do with it. That would make me really happy. So I thought I'd start off with my summary slide because there's a lot going on here, and I might just walk you through this first, and then I'll go through the details and return to it at the end. So again, I'm looking at eutrophication-related conditions and influences. So I'm working with data from a period from 2005 to 2019. And this summary slide starts at the top with river flow. River flow is really an important factor in terms of interannual variability. The black line here is river flow mean during June to September. And what you notice about that is that there was a change after 2013. We haven't had very many wet years at all. Actually, no years comparably wet to several of the years 2013 and earlier. The purple curve here in this top frame is the bay-wide load of total nitrogen from all sources to Narragansett Bay. And you can see that it follows the river flow pretty closely. And you can also see superposed on that, on the interannual variations, is a long-term decline, which is associated with these upgrades to the treatment plants. And just want to point out that that decline, the magnitude of that decline is comparable to the interannual variability itself. And that has made it difficult to clearly detect changes in the bay. But I think at this point, we have enough years of observations that we are able to see some of these changes. Okay, so the next couple of frames here are chlorophyll. I want to highlight that I'm using two different data sets here. They're complementary. One of them is the more fixed site observations, a time series, highly resolved temporally. And the second data set is the vessel-based surveys that cover the bay about between 5 and 8 times per summer. So they're less frequent, but they do have a better spatial coverage than the moorings. So these two data sets are complementary. So I'll just highlight the first frame here is chlorophyll conditions, and it's analyzing the data sets relative to severe thresholds. So that would be very high chlorophyll levels. And you can see the variability does sort of parallel that of the river flow and the nitrogen load, including a long-term decline. And that's true not only for the high thresholds, but also for the moderate thresholds, the second green frame here. And it's true for both the data sets, both the moorings and the spatial surveys. So the next, the bottom two frames here in red are the hypoxia conditions. They're analyzed similarly using both data sets and using two different thresholds, severe and moderate. And with hypoxia, you see that there's definitely been a reduction in hypoxia. It's much less severe in the most recent few years. And this is most notable after 2013, which was the most recent wet year, truly wet year. So this is the overall picture, the summary slide. Basically, the take-home message is that it seems pretty clear that the managed load reductions that occurred over a period of time have resulted in reduced chlorophyll and reduced hypoxia. Okay, so let's dive into the talk now after I've presented my summary slide. Hopefully I've got some time left. The presentation today kind of has two parts. The first part is all going to be bay-wide conditions, quote unquote bay-wide. I'll explain what I mean by that as I go through the slides. But that is what I just summarized. Those were all parameters that are meant to be capturing the conditions across the entire bay. And I'll talk about nitrogen loads, I'll talk about chlorophyll, I'll talk about hypoxia, and then I'll talk briefly about other physical influences like stratification, winds, tides, and then I'll point to what might be smart next steps. And then the second part of the presentation will be a closer look at Mount Hope Bay, which should tie in with the speakers that will follow me. I do have in the report a section talking about long-term trends, which I wanted to mention, looking at various different data sets in the bay, looking long-term trends in temperature, salinity, and stratification. I'm not going to talk about that in much detail today. I'll just touch on it a little bit, but if you're interested in that, it is in the report. Okay, most of us are familiar with the bay. I don't think I need to go through this slide in too much detail, other than just to review some of the basic characteristics of the bay. It's a temperate mid-latitude estuary. The hypoxia situation is during the late summer typically, and it's periodic. We have events that last between 2 and 7 days, several events each year in a typical year when hypoxia is present. And the flushing time scale is about a week to a month. The hypoxia is most severe in the north and west. So if you look at this map on the right here, it tends to be in the northern and western portions of Narragansett Bay. It's not a simple structure. The bay has some complicated coastlines, some islands, and a lot of embayments. It also has rivers coming in several different locations, which makes things a little bit complicated to analyze. And of course, many different treatment facilities discharging directly to the bay, and many of them discharging into tributaries upstream. So it's a relatively complicated setting. And when we talk about the Mount Hope Bay story, this of course is where that's located geographically, but I'm going to talk about nutrient load coming down from the Taunton River. So I just thought I'd highlight that real quickly. Okay, so we're going to focus on nitrogen loads for several slides here. This is a view of the entire watershed, including the bay as well as the upstream areas. And the history of this, as many of you know, in 2003, there was a fish kill in Greenwich Bay, a shallow embayment. And this led to a lot of attention and a public response in support of a law to require reduction of wastewater treatment facility loads. So the treatment facilities embarked on upgrades to their treatment. And this occurred over many years. The earliest, I believe, was in 2004. And the most recent major reduction was in 2013 to 2014. So these improvements are enacted typically from May to October when compliance is required, which makes sense with respect to the loading and the hypoxia in summer. I created a daily time series of bay-wide nitrogen load. And I did this using data sets from plants and rivers and lots of different sources. The load is broken into 18 different sources. 11 are plants that discharge directly to the bay. These are the blue rectangles here. 6 sources are rivers. They're the diamonds on this plot, different colored diamonds, and they are rivers that include the load from the upstream plants, but the load is calculated right at this location where the rivers are sampled, shown by a diamond. So for example, this diamond here in the Taunton River, we calculate a load there. It includes the upstream wastewater treatment facilities, all these red dots up here. The time series I created is daily. I wanted to do that because, again, the hypoxic events tend to last up to a few days or so. And I did treat total nitrogen, not other constituents. This is kind of in line with past budgets that have been done by Narragansett Bay Estuary Program. And so the calculation is simple load is flow time concentration. And what's interesting is that the flow measurements typically, which are daily, are much more frequent than concentration, which is a bit of a challenge, but the variability in the flow is much larger than the variability in concentration. And as a result, if you just linearly interpolate between your concentration measurements, which are infrequent, the variability in the load is generally captured because you do have daily flow measurements typically. So the flow dominates the variability in the load, not the concentration. And I did compare these results on an annual mean basis to prior budgets that were done and found pretty good agreement. So I think they're adequate and they can be used for the kinds of things that I'll be showing you today. And I just wanted to point out, I'll show a slide later where I take the sources west and east of Mount Hope Bridge and compare them to each other, just in the spirit of taking a closer look at the Mount Hope Bay conditions. So here's an example of one treatment facility, Fields Point. You can see here I have flow measurements on the bottom panel, concentration in the middle panel, and the load is their product up top. And so you can see for this particular facility, the upgrades were in 2012 to 2013. You can see a very clear drop in concentration during those years and corresponding decrease in the load during those years. So this is a plot showing all the sources, all 18 sources superposed. I'll just draw your attention first to the black line, which is river flow. All the other lines here are various different colors, are each of the 18 sources that I mentioned. And some of the big take-home points here, of course, for river sources, the intraannual variability is very high and matches the river flow data quite closely, with a long-term decline superposed. Different sources decline during different periods. That's one thing I want to highlight. Buckland Point is shown in yellow. The decline there was around 2004, 2005. The prior slide was Fields Point. This is light green color. You can see that decline was later, 2012, 2013. Overall, there is a sense of a long-term decline across all the sources. And just to highlight the Taunton River and its upstream wastewater treatment facilities, that is the largest of the sources, of the 18 sources on average across this entire time period. It's the blue line here. And it varies clearly together with river flow, of course. There is not a long-term decline that is apparent for that source, for that large source. So if you sum up those sources and you look at the bay-wide load, this is what it looks like compared to river flow. River flow, again, in black, nitrogen load in purple. I showed this earlier during the summary slide. And if you break this into two periods, before and after 2013, something kind of interesting shows up. You do a correlation kind of a plot here with TN load upward on the left axis, river flow on the right. You see that the two periods kind of have a reasonably tight correlation before and after 2013 with a different correlation, which is an indication that the load has come down as a result of these treatment plant upgrades. So for comparable river flow in any given year prior to 2013, you had a higher load than in years after 2013. Now this is, there are a few years after 2013 that have have river flow that was very wet, a few wet years, but the river flow is high enough, sufficiently high, that I think we can still see that there has been a load reduction. So that was the nitrogen load. We'll talk about the chlorophyll response next. And again, I'm using two complementary data sets, which I mentioned. One is the fixed site time series that's shown here on the left map. This is a data set which involves very dense temporal sampling. Every 15 minutes, we get a sample. And the sites, there are 8 sites shown here highlighted in purple that I'm using when I say bay-wide. That's what I mean. In this case, I am not using the Phillipsdale site, Sally Rock site, or the Greenwich Bay site. The reason is that they have their own rather independent variability, which is obvious when you look at the records. And it's not very coherent with the variability of the rest of the stations. So it doesn't make sense necessarily to pull them in and treat them, to group them with these others. Most of these mooring sites are in deeper locations, kind of on the channels in the bay. And there is a mooring in Mount Hope Bay. That's the characteristic of this time series data set. In contrast, the vessel-based spatial surveys over here on the right, I'm showing where locations are sampled. These are surveys that occur between 5 and 8 times each summer. So they're much less frequent. However, they do give better spatial coverage across both the deeper and the shallower parts of the bay. And in contrast to the time series, they don't have any sampling in Mount Hope Bay. So keep these things in mind. These are complementary data sets. They're not, they have different strengths and weaknesses. And so it's interesting that in comparing them, they're basically telling us the same story about the bay. And that's a nice way to get some confidence that it's in your results. So I'll talk about the time series observations and how they're analyzed and what the metric is here. We call it an index, the chlorophyll index. So you take your time series from an individual mooring site. The blue line here is the time series of chlorophyll concentration throughout the season. You see these events when chlorophyll concentration increases and then falls back down. There's a threshold. So the index is always defined relative to a threshold, shown here in red. And the index, what it is the sum of the area under each of these event curves for the entire season. So it's the sum of the areas marked in green here. That's what the chlorophyll index is. So it's basically area under the curve. It's analogous to degree days if you're familiar with the agriculture practices. And the units are micrograms per liter days. And you can refer to that as a surplus duration. That's sometimes the language is used. So an example is if you have concentration that goes 10 micrograms per liter above the threshold and stays there for 3 days, the surplus duration is 30 microgram liters a day. And so that's how we incorporate, this is a metric that incorporates the influence of how many events there were, how severe they were, how long they lasted. It's a season cumulative surplus duration of all events during the season. I'll talk a little bit about the 2 thresholds here. There's a severe threshold, 17.6, and a moderate threshold, 9.4 micrograms per liter. And these are the 80th and 50th percentiles of the chlorophyll measurements from all stations, all years. Okay, so the way that we take these this index result from we can average it across multiple sites, and that gives us a bay-wide indicator. So in my plots, I'll be showing the bay-wide index, and it's the result across all of the 8 sites, all the 8 time series sites, excluding, as I mentioned, the shallow embayments, which are Phillipsdale, Greenwich Bay, and Sally Rock. The second metric is the percent high chlorophyll. This is from the spatial surveys data set. In this case, the concentrations from all the sites are mapped across the entire sampled area. Basically, it's kind of a shore-to-shore coverage, better coverage than the time series. And the metric is the percent of the area that's above the threshold relative to the total area sampled. There are 2 thresholds in this case as well, severe and moderate. In this case, they're the 80th and 50th percentiles of the spatial survey data set. So they are higher, the thresholds are higher, 27.4 and 14 micrograms per liter. They're higher because the spatial surveys sample shallow areas where chlorophyll levels are higher. So in this case, we have 5 to 8 surveys in a given summer. We take that percent area metric for all the surveys and average them. That's our seasonal metric. So in terms of results for these 2 metrics, you can plot the index versus the nitrogen load. or the percent area versus nitrogen load. And you can do it for severe thresholds, which is shown on the left plot, or moderate thresholds shown on the right plot. And you see that there's a pretty good correlation, kind of what we'd expect: higher nitrogen load, higher chlorophyll. And so, you know, this kind of quantifies the relationship. The correlation is not as tight as between nitrogen load and river flow, but still there's a clear correlation. And it's true for both thresholds and both data sets. And this is what the results look like in terms of time series. This is, again, just kind of reviewing what I covered in my summary slide up front. And you can see this interannual variability with this long-term decline superposed for both data sets and both thresholds. Interestingly, the last 2-3 years or so, the chlorophyll has remained relatively low, whereas the load has crept up just a little bit. And so there may be a lag in response in the bay. This is true also of 2013. 2013 was a year when the load had come down substantially, and the chlorophyll didn't necessarily yet. It took a year or two after that. So there may be a lag in the system here. It's an important thing to try to understand better. Okay, the hypoxia response is investigated in very much the same way, the same two data sets. In this case, I'm using oxygen measurements, and they're from the near seafloor depth, not the surface. And in this case, the index for hypoxia is essentially inverted. It's the area swept out by the oxygen measurement curve below the threshold. But otherwise, it's the same principle. The units in this case are milligrams per liter day. And the percent area hypoxic is calculated the same way using the spatial surveys. In this case, for oxygen, the thresholds are the same for both of the data sets. And these are thresholds based on harm to organisms that are used in a regulatory context. The severe threshold is 1.4 milligrams per liter. The moderate threshold is 2.9 milligrams per liter. And so again, a sort of a scatter plot approach here. This is parallel to the one I showed you for chlorophyll. In this case, we're showing both metrics, the hypoxia index and percent area, and we're showing it for severe and moderate thresholds. You can see for the moderate thresholds, there is a correlation. It's not as tight as chlorophyll again. And so this kind of makes sense if you think of conceptually, you think of nitrogen load, which is affecting chlorophyll, and then chlorophyll, which is affecting hypoxia. You would expect these correlations to be getting less and less tight as you move down that sequence of factors. And that's what we see. So interestingly, the severe thresholds case, there are a lot of zero values there. So I didn't actually run the correlation for that left frame there. But in terms of the time series, this is what they look like. And you can see that hypoxia is definitely different in the years since 2013 compared to the years before 2013. If you look at these years before 2013, we had some fairly severe hypoxia, both moderate and the severe thresholds, some quite high peaks here during the years, especially when river flow was high. And in 2013, we had high river flow, but the nitrogen load had come down somewhat. Hypoxia still was severe that year. So again, this points to that lag in the system. And yeah, so in the most recent years, the most recent several years, hypoxia has come way down compared to what was happening back in the 2000s. Okay, so I'll talk briefly about some physical influences. The stratification could be playing a role. And so I used the fixed site time series to compute stratification. And it is actually quite closely correlated to river flow. In fact, more tightly correlated than the load is, because of course there is not a long-term trend in stratification as there is in load. It turns out there is a long-term trend, but it's a very weak one. And so I think that stratification is not as able to explain the long-term declines in chlorophyll and hypoxia as the nitrogen load is. So while stratification may be necessary for hypoxia to occur, I think it's the driving factor here really is the load, and stratification is secondary compared to load. This scatter plot down below here, I use all years here, they're grouped together. There's a nice tight correlation. So before and after are similar. Before and after 2013 are similar, unlike the load, which I showed earlier. And this is a slide showing various other physical influences, and including temperature, wind speed, wind direction, tidal range, and the sea level difference between Providence and Newport. And again, I was kind of looking for something that might have a telltale long-term trend that might explain the chlorophyll and hypoxia. Essentially in temperature, you definitely see a warming and a long-term trend in temperature, which likely is causing the metabolic rates to increase and could be a reason why the hypoxia is declining at a slower rate than it otherwise would due to these plant upgrades. And in terms of wind speed, wind direction, tidal range, sea level difference, none of these really give a nice long-term trend that could potentially be playing a role here. There is a little bit of a long-term trend in the tidal range, which you might expect a higher tidal range to perhaps reduce stratification and somehow play a role in hypoxia. However, as I just mentioned, there's really not much of a trend in stratification. So even though the tidal range trend is present, it does not seem to be affecting stratification. So I conclude that the physical influences are having a much more minor role compared to the nitrogen load. And here I've arrived again at my summary slide. So again, this just kind of restates all the things I've been trying to relay in a very concise way on one slide. Chlorophyll and hypoxia have declined, and it's apparent that it's associated with the managed nitrogen load reductions that have occurred. So I think we have an opportunity now to analyze this most recent summer, which was extremely wet, and will be a great test of the extent to which the bay really has changed. It's the first truly wet year, I believe, since 2013. And so that's an obvious next step here. Another next step would be to look more closely at why there seems to be a lag in the response of chlorophyll and hypoxia relative to changes in nitrogen load. And lastly, I think it would be interesting to go back and look more closely at the higher variability and the completely independent nature of the variability in the shallow embayment sites, the Seekonk River and Greenwich Bay, which again, as I mentioned, were excluded from the quote unquote bay-wide conditions when treating the time series observations for this analysis. Okay, now I've got a few slides to transition us towards Mount Hope Bay focus. And the first one is just looking at the Taunton River and its upstream treatment facilities, the load for that source. Remember, this is one of the 18 sources that were treated in the bay-wide load analysis. And for this particular source, the decline in concentration really is not apparent. And of course, load follows that. So this is an interesting point where many of the other sources do show clear declines. The Taunton River and its upstream facilities does not. I think I mentioned that earlier. This is also looking at the nitrogen load. This is the sources to the west and east of Mount Hope Bridge. They're superposed on river flow in black. And so it's kind of what you expect as based on what I showed earlier, the west sources. There are many more of them west of Mount Hope Bridge. And so the load is higher, but their variability has interannual swings corresponding to river flow with a long-term decline, a very clear long-term decline superposed. Whereas the sources to the east of Mount Hope Bridge, which consist of three, the Taunton River upstream facilities that I just showed you, in addition to the Fall River treatment facility and the Somerset treatment facility, the sum of those three sources is not showing as clear of a decline. There's a weak decline, which is apparent. And I believe that's due to the Fall River plant. So this just gives you kind of an interesting look on Mount Hope Bay and how its load has been changing in comparison to how much the load has been changing in other parts of Narragansett Bay. This is a look at the chlorophyll index and the hypoxia index for that mooring site in Mount Hope Bay, just isolated from all the others. And you can see here the background gray bars are an indication of how wet the river flow was in any given year. So you can see prior to 2013, there was a pretty clear pattern with higher chlorophyll and higher hypoxia during relatively wetter years. The pattern's not as clear here in Mount Hope Bay as compared to the rest of Narragansett Bay. And so there's variability here that's independent from the rest of the bay. And also in most recent years, this mooring does not have hypoxia, at least not for the moderate threshold. And the last few years, there has been a decline in that chlorophyll index. So there's some variability here, which is independent from the rest of the bay. And this will be the last slide I show up. Just wanted to show you a little bit of the work I did on long-term trends. This is using the fixed site time series data set and all the different locations, all 11 locations. Each frame here is one of the locations, and the bathymetric depth is shown in parentheses. So we're going from shallower to deeper. This is Phillipsdale, Sally Rock, Greenwich Bay, Mount Hope Bay, Bullock's Reach, the T Wharf, Connecticut Point, Mount View, Quonset Point, Hopsquash Point, North Prudence, and then at the GSO dock. And in each frame, there's two bars here shown. The solid bar is the near surface measurement. The open bar is the near seafloor measurement. And the uncertainties here are showing you the statistical confidence is not super strong on these. It's kind of marginal. But if you look just at this 2006 to 2019 period, when all the data sets I analyzed had, it was a common period to all of them. You do see warming, which is consistent with what's been seen in other data sets across the region. It's about a ½ degree per decade. That's these solid bars here. And at the seafloor, you also see warming. And there's a pretty clear pattern that the warming is faster near the seafloor. In fact, if you average across all these sites, I believe it's approaching 2 times as fast, which is interesting. I think that's likely associated with offshore waters coming into the bay at depth. And so the one thing I wanted to highlight here is how unique Mount Hope is, this Mount Hope Bay site. All the others are showing warming, both near the surface and the seafloor. At Mount Hope Bay, there's cooling. In fact, during the 2006 to 2019 period, there's cooling. And this, I think, is due to the discontinued power plant, which happened around 2012, right about in the middle of that period of time. And so that was influencing the heat budget overall in Mount Hope Bay. So that is the last of my slides, and I think I'm just about on time.
Thank you, Dan. So keeping this going, we're going to keep moving along, and I'm collecting these comments in the chat for questions later, so keep them coming. But in this, what I'm going to do is highlight Corinne and Jane, and they are going to start their talk. So while they are uploading, they're going to show us how they examine the effects of the Brayton Power Station on Mount Hope Bay Finfish communities and what this means for their integrated reporting. So Corrine is a principal biologist with the Rhode Island Department of Environmental Management, the Division of Marine Fisheries, and she manages the state's eventless trap lobster survey, while Jane is a supervising environmental scientist with Rhode Island DEM's Office of Water Resources, and she supervises the Monitoring Assessment Standards and TMDL's group. So we are now shifting into the practical application of all of these wonderful data sets. So with that, I will let them take it away.
Real quick, can you just confirm that you can see my presentation as a slideshow?
I see it, looking good.
Thank you.
All right, so I will start off and shift us a little bit more back into Mount Hope Bay. So thank you for the opportunity to present today. And I'll start us off with a very brief regulatory history of Brayton Power Station's impact on water quality in Mount Hope Bay, and then turn it over to Corinne for a deeper look at the Finfish community impacts. So I probably won't do the Brayton Point story justice. We could probably spend a whole hour and a half just talking about the regulatory history of Brayton Point. So if you feel like I've left some parts out, there's definitely more that could be discussed, but I will just be hitting the highlights. So next slide. So DEM's Office of Water Resources, our work falls within a water quality management framework. So it's a very circular process where we are continually monitoring, collecting data, evaluating data and information to protect, maintain, and restore Rhode Island's waters. Today, we'll walk through an example of this process in Mount Hope Bay that was years in the making. Next. So as Rhode Island's Water Pollution Control Agency, DEM is delegated to implement the Federal Clean Water Act. The Office of Water Resources carries out the steps for a State of the State's Waters Report, which is required under the Federal Clean Water Act biannually. So our office, we establish water quality standards for the state's waters, which includes setting goals and how to measure our progress on those goals. We're required to monitor, assess, and report on the water quality conditions of all Rhode Island waters. We're also required to develop the list of impaired waters, waters that are not meeting our goals, often referred to by its Clean Water Act section name, the 303D list. We also set a schedule for something called a total maximum daily load, a TMDL, which are water quality restoration studies for all waters that are on our 303D list of impaired waters. Next. So one of the water bodies that we regularly assess and report on its condition to EPA and the public is Mount Hope Bay. Mount Hope Bay is a shared water body with Massachusetts. And the red star in the smaller map is its general location, as we've heard about today, and with the inset map showing a closer up view of this area. And the red section denotes the Rhode Island portion of Mount Hope Bay. And for our purposes for the Clean Water Act reporting, we divided Mount Hope Bay up into 4 water body segments. Next. Oops, back one. Okay. So upstream of the Rhode Island portion of Mount Hope Bay is the Brayton Point Power Station location, noted by the black outline circle with the red inner area. So at one point, it was the largest coal-fired generating station in New England. It began operating in the 1960s and was estimated to power 1.5 million homes using coal, natural gas, and oil as fuel sources. All units discharged heated water to a single discharge point along the western edge of the Brayton Point Peninsula. So over the years, various environmental concerns arose from the operation, but the focus today will be the thermal impacts on water quality and the finfish assemblage in Mount Hope Bay. Next. So as part of our biennial assessment reporting to EPA and the public, we submitted a 1996 draft 303D report to EPA. And this was primarily based on work of Mark Gibson of the Division of Marine Fisheries that painted a bleak picture of most of the finfish stock in Mount Hope Bay. And further analysis by Mark Gibson related the fish abundance to heat rejection from the plant. Additionally, the once-through cooling system damaged or killed many aquatic organisms by entrainment and impingement, in addition to elevating the water temperature in Mount Hope Bay. So a fish bioassessment impairment was added to the Mount Hope Bay segments. And a few cycles later, water temperature was also added as an impairment cause. Next. So in 2003, October 2003, EPA issued a NPDES discharge permit with strict thermal limits requiring approximately 95% reductions in flow and heat for the Brayton Point Station. Dominion, who operated Brayton, reached an agreement with EPA to cease all permit litigation in 2007 and convert to a closed cooling cycle system to comply with the permit. Dominion retrofitted Brayton Point Station's existing open cycle cooling with a closed cycle cooling system. The 4 heating units were converted to closed cycle cooling and began operating as such beginning in October of 2011. The last unit was brought online in May of 2012. These almost iconic towers were formerly evident from the highway prior to their demolition. So below the picture of the cooling towers, you'll see a graph depicting the annual heat load And you'll see that following the cooling towers, a sharp drop in annual heat load was evident. So in our 2016 cycle, Dave Borkman and our shellfishing group did an excellent analysis of the monitoring buoy data in Mount Hope Bay to demonstrate that the Rhode Island segments were meeting Rhode Island's water quality regulations for water temperature. EPA agreed with this assessment and approved the removal of the water temperature impairment. Next slide. So after the removal of the water temperature impairment, we were left with the associated fish bioassessment impairment. So the Office of Water Resources requested the Division of Marine Fisheries assistant, given their extensive data sets and statistical expertise. So at this point, I will turn it over to Corinne to pick up the next piece of the story.
Thanks, Jane. So I'll get right into it. So as mentioned, the Office of Water Resources came to the Division of Marine Fisheries to conduct fish bioassessments in Mount Hope Bay after the power plant was decommissioned and after the cooling towers were installed in 2011. We were fortunate to have work that was done by Mark Gibson, published in 1996, which had led to the EPA permit being altered in 2003 for Brayton Point. So we were able to revisit the analyses that were conducted by Gibson back then and use that as kind of a framework for the analysis that I'll be presenting today. So as mentioned, he found in this report that there was a significant decrease in aggregate finfish abundance in Mount Hope Bay that was concurrent with an increase in water, heated water effluent release at Brayton Point. There was an 86% reduction between the period before 1984 to the period after that. And that time period, 1985, aligns with when there was a 45% increase in heated water effluent being released at the plant. So just to go over the timeline of the plant briefly again, just so we can contextualize the results of the analysis we had conducted. Plants commissioned in 1963 with the installation of 4 units over the next about 20 years. Unit 4 was installed in 1985. That's when we see an increase in heated water effluent by about half or 50% increase. So we see a transition from this medium flow period, as I call it in the yellow, to a high flow period that starts in 1985. That continues until 2011 when we have the cooling towers start to be operational. And that's when we have the low flow period in green here, where there's no heated water effluent being released at Brayton Point. So our mission again was to revisit the 1996 assessment that was conducted by Mark Gibson to re-examine the effects of the power plant on finfish abundance in Mount Hope Bay. And assuming we see those effects, to see whether there's evidence of change or recovery in the finfish community since those cooling towers were commissioned and since the plant was decommissioned. So one thing we have to really seriously consider when we're approaching analyses like these is how we can examine change and recovery in an ecosystem when we know that there is change occurring in the ecosystem as a whole over the long term. So we're looking at data sets that cover about the last half century. And we know from many articles, including those that I've highlighted here, that there's been change in the environment over that same time period. So we've had temperature increases, and we've also had a change in the finfish community in Narragansett Bay. Generally a shift from colder water species, demersal species, to warmer water and pelagic species in Narragansett Bay. So we are concerned with how do we assess recovery, especially in an ecosystem where we're seeing change over the period of time that the plant was operational. And so our approach here was to use Narragansett Bay essentially as a control ecosystem for analyses. So we're interested in looking at the changes that have occurred in Mount Hope Bay over the last 40 years or so and comparing that to Narragansett Bay as an indicator or as a signal for what's going on in the environment in Southern New England as a whole. And we're really fortunate in Narragansett Bay to have long-term monitoring surveys that have been conducted in Mount Hope Bay and within Narragansett Bay as a whole by local institutions, organizations, and governmental organizations. So for Mount Hope Bay, we have a trawl survey that was conducted by Norman Doe Associates, which was contracted by Brayton Point to conduct this monitoring survey. They collected data from 1972 to 2014 monthly at 5 stations in the upper Mount Hope Bay. And then for the rest of Narragansett Bay as our control, and here's a map of our stations, we have the Division of Marine Fisheries seasonal trawl survey, where we have 10 fixed stations indicated here in orange, plus 14 randomly selected stations that are sampled every year, or they're redrawn every year, excluding Mount Hope Bay stations because we're using this to compare what's going on in the rest of Narragansett Bay. And then for each of these trawl surveys, we're taking the 30 most abundant species, or the species that are most prevalent in Mount Hope Bay, to remove those species that are really sporadic and occur only potentially once over the course of 4 years. And then we want to be able to assess the effects of the power plant operations. And so we needed some way to quantify what the power plant operations level was, or what the level of heat input, because that's our main concern here, was. So we used, Jane had shown this before, but billions of gallons per day, the amount of heated water effluent being released from the plant as a proxy for increased temperature. So it's counterintuitive, but a higher level of cooling water flow is associated with higher heat output. The more water they're taking in to cool the generating units of the plant, the more heated water you're having released back into the bay. And that water, I should have mentioned, was generally released at a temperature 7 to 10 degrees Celsius above ambient. So we have two main questions here in examining finfish community in Mount Hope Bay as it relates to Brayton Point. The first is aggregate finfish abundance, so the total number of fish that we have in Mount Hope Bay. What that looks like over time, how that relates to plant operations. We approach this using time series modeling techniques. The second question isn't so much about absolute numbers of fish, but community species composition. So which species are present and what's the relative proportion of each of those species in the community. And we use a technique that I'll explain a little bit in the following slides. And again, we're comparing the changes that we see in Mount Hope Bay with the changes in the rest of Narragansett Bay. So looking at the results of our time series analysis of aggregate finfish abundance, this is showing you Mount Hope Bay, and the blue line is a time series model that we fit after fitting a suite of time series models that provided the best fit to the data that we have. Essentially, the takeaway is that abundance overall significantly changed in 1984 and 85, and then again around the time period of 2010 to 2011. And we can see in the plot here, we've highlighted in yellow, red, and green in the background those phases of plant operations that I highlighted before, so medium, high, and low flow phases of the power plant. And we can see that the changes in abundance in Mount Hope Bay align with the changes in plant operational regimes. When we look at Narragansett Bay, same data, or the same data type, excuse me, you can see in Narragansett Bay, it's highly variable in terms of the aggregate finfish abundance, but you have kind of a steadily increasing trend over the time series. So you don't have these really sharp changes, stationary phases of abundance in Narragansett Bay that you're seeing in the rest of, or in Mount Hope Bay. And we'll revisit that again, but we're moving into species composition analysis. So how does the makeup of the finfish community in Mount Hope Bay change over time? And we do this using a technique called non-metric multidimensional scaling, and I won't get into the weeds on this, but I think it's worth kind of walking through heuristically how the technique works so that we can contextualize the results that we get from doing this analysis. So NMDS allows us to simplify data or collapse it, data with many dimensions, so that we can make comparisons a little bit more intuitively. So the data that we have here are essentially this big data frame where you have all of the years of our data, and then you have a column for every species that we see. So we have 30 columns of data for all of those years. And if you're trying to brute force look at this and do this type of analysis, it's going to take you a really long time, and it'll be difficult to kind of parse out trends and understand what's significant here. So NMDS takes a data frame like this, like what you have on the left, and it configures it so that it is plotting it in two-dimensional space here. So if we have the years of our data, NMDS allows us to get this plot where you have years 1, 2, and 3 in the top left corner, 4, 5, and 6 in the bottom right corner. Distance in the plot is a proxy for similarity between points. So years 1, 2, and 3 are similar to each other. Years 4, 5, and 6 are similar to one another. And then those two groups are different from one another. And so we're moving into the next slide will be the actual data that we have. So this is the data that we have from Mount Hope Bay and Narragansett Bay, and I'll walk you through it. We have Narragansett Bay, all years of data from 1985 to 2014 in gray. And then in the color the colored points are from Mount Hope Bay, where we have 1980 to 1985, the medium flow period in yellow, high flow period from 1986 to 2009, and then the low flow period from 2010 to 2014 in blue. And when we get this 2D plot, as I was mentioning, points to get close together are similar, points far away are different. You can see that there's this tight association between Narragansett Bay and Mount Hope Bay for the medium flow phase in the beginning in yellow. Then you see this really large disparity. There's a diversion between or discrepancy between Mount Hope Bay and Narragansett Bay, where you see the points in red, the high flow phase of the plant. Once we have the low flow phase after the cooling towers are erected, we have more of an alignment between Narragansett Bay and Mount Hope Bay in terms of the species composition or the relative proportions of species in Mount Hope Bay and Narragansett Bay. And what's really interesting, so we see this dominant signal of the plant kind of showing you that it's driving, potentially driving those differences in species composition between years. But what we're also seeing in this plot, and I'm plotting it again here, it's the same exact data in different colors. So you have earlier years in pink, later years in blue, and you're seeing this steady shift from early years to late years in the vertical. So things are changing slowly. The points are moving kind of down the plot over the long term, over the time series. And so we're interpreting this as a steadier change that's happening in the ecosystem, and it's happening in both the Mount Hope Bay and the Narragansett Bay data sets. And this is a signal that we've seen and that has been published, and it's highlighted in those articles that I showed earlier, this transition from cooler water demersal species to warm water pelagic species. So window pane, winter flounder, cunner, hake species are more prevalent in the beginning years, and then we transition to an ecosystem where we have more sea robin, scup, black sea bass, butterfish. So we're seeing that signal, and it's neat. You can see the signal in the plot that we have in the analysis that we're conducting, and you can also see that signal of the power plant kind of dominating the differences that we're seeing. And if we look at species-specific trends, we can kind of contextualize and understand specifically what's going on and kind of bring in the results of the abundance data and of the species composition data. So if we're looking at cold water species here, just a couple of examples, we have cunner and we have winter flounder. At the top, we have Mount Hope Bay in purple. In the bottom, we have Narragansett Bay in green. And so what we're seeing here is that both of these species decline over the time period from 1972 to 2014. But the specific time when that decline occurs is right at 1985, right in the middle of the 80s, right when we have that increase in heated water effluent being released at Brayton Point that Gibson had highlighted in that report in 1996. And then in the rest of Narragansett Bay, you don't see that decline happening so much right then, but it's drawn out over a longer period of time over the time series. So these species decline in the ecosystem in general, but the specific timing of that decline aligns well with power plant operations in Mount Hope Bay. And conversely, if we're looking at warm water species, you can see that in Narragansett Bay, you had an increase in scup and black sea bass in the green over a more prolonged time period. It kind of starts in the 90s and early aughts. And then for Mount Hope Bay, you see increases or you see big upticks in those species, but only after the cooling towers have been erected. So bringing everything together, you can see that looking at the abundance and species composition data, we see the strong signal in Mount Hope Bay that does align with those phases of plant operations at Brayton Point. The abundance has a severe downtick. It's really low for the high flow period of the plant. And then we have an increase in abundance in more recent years. The specific species that are accounting for those increases in abundance at the beginning and the end of the time series are different from one another. So the Brayton Point Power Plant signal seems to mask what we're seeing in the rest of Narragansett Bay for that transition that happened over those 4 decades. So Narragansett Bay was seeing a slow shift in its dominant species over that time, and that shift in species composition is not evident in Mount Hope Bay until we have the cooling towers erected. So we see evidence of a recovery in abundance, but the community has shifted in Mount Hope Bay, and it really highlights that when we're looking and trying to assess recovery in an ecosystem for purposes such as this, really have to contextualize what it is that recovery looks like and what does it look like in the rest of the ecosystem of interest. Because if we were to look for the same species, recovery in the species that were dominant back in the 80s, you just wouldn't see it in Mount Hope Bay, and I don't know that you could expect to see it, or it wouldn't be reasonable to. So in summary, we see that high heated water effluent flow at Brayton Point was associated with low fish abundance in Mount Hope Bay, but that recent abundance and species composition of Mount Hope Bay more closely resemble the rest of Narragansett Bay than they did during the pre-cooling tower period of the plant. So with these results, Mount Hope Bay was recommended to be delisted as an impaired water body for fish bioassessments as of spring 2020. And Jane can speak a little bit more to this. The EPA approved Rhode Island's 303D list February 17, 2021. It remains impaired for nitrogen, dissolved oxygen, and pathogens. So thank you very much. I appreciate the opportunity to present and be happy to take questions, I think, or I'll hand it back to Courtney.
Thank you to Dan, Jane, and Corinne for these awesome talks. While everyone here, if you would like to show your video or raise your hand to ask your question, that we can handle that. But what I'm going to do is go through the chat and I will give you 3 of the questions. And then while others are thinking of new ones. All right. So the first one, our first question was from Dan, and it came from Jim Hagee at EPA. And he was wondering about your thoughts on the point source load estimation and using egret from USGS rather than Beals or what you used to estimate your loads. Dan, you're muted still.
Yes, thank you. I can speak to that briefly. I have not looked into egret. I'm not familiar with that package. So it might be a good thing to do. And the method I used is as I described, it's kind of a brute force, simple linear interpolation of the concentration data, which are much less frequent, and then multiplying that by the flow data, which typically are daily. And I did comparisons of the output to the results from Beals estimator that were done and showed that the agreement was reasonably good. So it might be worth a look to approach it from other established methods such as egret. I have not done that.
Thanks, Dan.
Sure.
I could help you out with that if you want to look at it.
Thanks.
All right. So the next question, again, was for Dan. Do you think you could detect a total nitrogen signal from the initiation of the CSO runoff tunnels from Fields Point? And that's from Giancarlo Giacchetti.
I have not looked for that. I would have to learn more about what measurements are made at the plant in terms of the CSO flows, where they go, and whether they track the nutrients. I am not sure if that passes through the same outfall that for which I have looked at the data, and I'm actually not even familiar with the date range I would look for it. And so, I mean, I think it would be an interesting thing to look into. What I did is described in the report. If you wanted to pull up the Fields Point plot and take a look at it and sort of look for that evidence of some kind of change during when the CSO tunnel came online, that would be one starting point, but I'm not sure that the data set I was using would actually show that.
So from what I know, Dan, about the Fields Point work for the tunnel is that the tunnel is just basically a giant holding container that funnels all that stormwater to Fields Point to be processed through their typical system. So it would come out of the same outfall pipe that you get the data from, but it was done primarily to handle bacterial loading. And I think the nitrogen is just an added bonus in that case. It came online about 2008, and they keep adding more interceptors. So they keep dumping more stormwater into it. So it would be interesting if we had a better comparison of pre and post tunnel for stormwater runoff, but stormwater runoff has been lacking as a true measurement. It's really hard to get at. So I think there might be something, but I think we could think about that.
Yeah, it'd be interesting to look into that.
And Jane, you have your hand raised?
I was gonna say some of the things you just said, but I will add, when we delisted Mount Hope Bay, we also delisted a portion of the upper Narragansett Bay for shellfishing use impairment, and part of that was we pointed towards the CSO tunnel coming online. So we are seeing some impacts and some positive things going on in the bay and in the pathogen side of things already, and we've documented that.
That is very good to know. Dave Monty, you have your hand raised.
Sorry about that. My question, I guess, is for Corinne. Being a charter captain and recreational fisher and fishing writer, obviously recreational fishermen are anxious to know what type of fish are in Mount Hope Bay. And composition-wise, it seems like they're very similar to what has changed in Narragansett Bay proper, and I think you sort of pointed that out. I think David Taylor sort of asked a related question in regard to fish abundance. So what fish seem to be in Mount Hope Bay in greater abundance? What species? Or is it pretty equivalent percentage-wise to what's in Narragansett Bay?
Thanks for the question, Dave. So I will say with the caveat that the data that was presented in this presentation, that survey ended in 2014. And the most recent years for that trawl survey indicated that black sea bass and scup were the numerical dominant. So they were most abundant in those years since the cooling towers were erected. I can take a closer look at our trawl survey data, which has stations in Mount Hope Bay, and let you know what specifically is going on up there in the present day. And I'd be happy to do that. But in doing these analyses, it seemed that those two species, black sea bass scup, were the most in that ecosystem, and there weren't any that were surprising given comparisons with the rest of Narragansett Bay.
Thank you.
Thank you.
So Corinne, I think there's a related question in the chat from David Ciochetta. Excuse me if I really butchered your last name, David. Can you distinguish a range or gradient in impacts on fish, or just as a bay total analysis?
Yeah, that's a really good question. So the stations that we had available to us are all located in pretty close proximity to the power plant. I think that if we could have gone back in time, you know, knowing how people prefer to do these surveys now, we would have done an analysis that allows us to sample on a gradient with distance from the power plant, where we could see those effects and see how far from the plant those effects are occurring. As it stands, we're not able to really distinguish a gradient. We can see those impacts that I highlighted at all of the stations. So that abundance pattern is happening at all of those stations that we have in Mount Hope Bay, but we don't necessarily see it like a gradient and impact from the plant. But I think that's just based on the way that the trawl survey was designed. So I think, yeah, again, if we could have gone back and done it differently, we might have been able to add more stations and have like a real gradient analysis done. We do have data from DEM as well, and that's at stations in Mount Hope Bay that are a bit further away from the power plant. So they're more in the southern portion of Mount Hope Bay. And those data are only collected sporadically through the time series, so we don't have them for every single year. And that signal is not apparent in those data, if that helps. But yeah, to answer your question, we aren't able to really see at what distance those effects are taking place and where it kind of, you don't see the signal anymore.
So those are all our questions from the chat. Please keep raising your hands. We can keep this chat open. For Corinne and Jane, what is the next step with all the data that you have from Mount Hope Bay? So since you've delisted it, what's the next analysis or next step you want to do to really understand the changes to Mount Hope Bay?
Well, I guess I'll start on the, on the assessment side of things. We still have some other impairments, so we will continue that within the assessment program to keep an eye on those, and depending on where we determine to do next TMDLs, things like that, that's where we would go next, at least for the assessment program.
Yeah, and I think for us, having these results come up really highlighted that, there's potential for there to have been a lot of change in Mount Hope Bay since the cooling towers were erected. And so I think for us, it's just kind of leveraging the data sets that are available and kind of seeing, like Dave Monty requested, to see what's specifically happening in Mount Hope Bay. And now that we've seen, this pattern of change, it would be interesting to be able to kind of see what data are available even since this analysis was done, because that trial survey, as I mentioned, ended in 2014. But there are other long-term monitoring data sets that might be able to be used to start examining what's going on in Mount Hope Bay.
All right, thank you. Any other questions? All right. So thank you. Oh, Eliza popped in. Please unmute yourself, Eliza.
Hi, sorry, it took me a minute to find the hand button. Question for Dan, can you go back to when you were talking about stratification and how you think it's secondary to total nitrogen load in terms of driving the chlorophyll and hypoxia impacts? Can you just review that again? It went kind of fast. And don't forget to unmute yourself too. Thanks.
Thank you. I didn't do a sophisticated statistical analysis. I'm just looking at the time series plots and scatter plots, and it's clear, even just doing that, it is clear that stratification is tightly linked to river flow. There's the long-term trend in stratification is very minor. And so the interannual changes in river flow drive interannual changes in stratification very directly. Whereas the nitrogen load is also varies interannually parallel to river flow, but has a long-term decline superposed. And I think that it therefore can explain the long-term declines in chlorophyll and hypoxia better than stratification could. And so I think that perhaps without stratification at all, we might see a lot less hypoxia in the bay, because the hypoxia occurs at depth and stratification is necessary to isolate the deep waters from re-aeration through the air-sea interface. But having some stratification present is necessary for the hypoxia, but the change in nitrogen load is what has been really driving the changes in hypoxia. So hopefully that answers the question.
Yep, thank you.
So Dan, Candace popped another question into the chat asking, how does your total nitrogen input in your study compared with the previous budget inputs from Jason Krumholtz's dissertation or Scott Nixon's, the two budgets that he has done for Narragansett Bay?
Yeah, I looked at that and I did a comparison of the annual results from the prior budgets by just computing the annual average across my daily values across the 365 days of the year. And the comparison is, I think, acceptable. It's not perfect, but it's reasonable. I think it's defensible. I think there's a table in one of my reports that shows the direct comparison and gives you percentage differences between the two different methods. And as I recall, mostly they're in the 10 to 20% range in terms of the differences.
Okay, Dan, thanks.
My pleasure.
I just put the link to that extensive work from Dan in the chat. So Dan Dan helped out with Narragansett Bay Estuary Program State of the Watershed report, specifically looking at chlorophyll and hypoxia, and over the last 5 years has been building on that work through these different reports. And one of them was to do this time series analysis of total nitrogen. So I think nobody else has any questions. While you're thinking of it, I will just do my little speeches here, but thank you all for attending. This was the first webinar NBEP has hosted, and we hope to host more. So if you or your colleagues have any ideas that you would like to have in a larger audience, the Estuary Program is always looking for good science to share with our partners. Finally, for everyone here, I can also send a follow-up email with all of these links and anything, and Jane and Corinne can share any information they have on their work or other things that they would like to share out. So with that, I thank you all for this wonderful afternoon to spare some of the gloominess away by talking about awesome science in Mount Hope Bay. And I hope to see you all again soon with a future webinar. Again, if you have any questions, just contact us here at the Estuary Program. It's nbep.org. And I will talk to you all soon. Have a wonderful afternoon. And thank you once again to Jane, Dan, and Corinne for sharing your data with us.
Thank you for the opportunity.
Thank you.
Thank you.